All right, so the last two sections in this unit focuses on graphing a rational function. So when we are graphing a rational function, there are several unique elements to a rational function that come into play. So we're going to spend a lot of time going through those nuts and bolts and looking at how to do it. So a couple things that we already know how to do. First thing is the fact that there are two types of rational functions. There is a reciprocal function, which is given in this format, and then there's a standard rational function, which you have a polynomial at the top of the fraction, polynomial at the bottom. So there are two types. Since there are two types, there are different ways in which they have to be worked out, which we'll get into that very shortly. However, there are three elements to a rational function that are absolutely important. So, for instance, you can see here, there's your graph of a rational function. So it's not our normal curve. It's not a normal connected curve. There are two parts to the graph. Notice that there are two parts to the graph. So rational functions are split apart graphs, separated graphs. So first thing you'll notice about the graph, there's this line that's going down the middle of it. This vertical line going down the middle of it. So when you have a rational function, remember that there's one number that you can't divide by, and that's 0. So since you can't divide by 0, anything that would cause you to divide by 0 can't be used for this function. So there's a special name for that, called the vertical asymptote. The vertical asymptote is where the graph would be undefined. So the vertical asymptote determines the domain of the function. Vertical asymptote determines the domain. So, for example, if you look at this graph, you have a dotted line going through x equals 3. So that means your vertical asymptote will be x equals 3. What that also means is your domain is x cannot equal 3. So your domain for a rational function, you're telling what numbers you can't put in. Any questions before we continue? So keep in mind, your quiz this weekend does not include this section, although it could show up in the extra credit. So it could show up in the extra credit. So the next part is called a horizontal asymptote. Horizontal asymptote is the place of the graph where the graph flattens out. Where the graph flattens out. So notice that you have this curve that gets flat at a particular point, and you have this curve that gets flat after a particular point. So it looks like somewhere here, the graph gets flat. That is called a horizontal asymptote. Horizontal because it's going from left to right. Asymptote because the two curves don't touch that line. It looks like they flirt with that line, but they don't touch that line. They flirt with it, but they don't touch it. That's a horizontal asymptote. So in this particular example, the horizontal asymptote is y equals 1. So horizontal asymptote determines the range. So that means your range is y cannot equal 1. It can equal anything else, but it just can't equal 1. Any questions with horizontal asymptote? So the other part, the third and final unique element to a rational function is the idea of a point of discontinuity. A point of discontinuity is also known as a hole in the graph. So if you notice, there's a hole sitting in the graph. There's a hole sitting in the graph. That means that graph doesn't exist at that point. That one minute little point, it doesn't exist. So those of you who are going to calculus and going to pre-calculus, you will deal heavily with whether something is continuous or not continuous. Points of discontinuity and points of discontinuity. You're going to deal with that a lot in pre-calc and in calculus. So this is just a brief taste of what it is now. So that hole in the graph is called a point of discontinuity. So you would literally say that there's a hole at, and you tell what the point is. So this is -1, 0.5. So there's a hole in the graph, you just tell them where the hole is. Now in a second, in a little bit, you'll see how do we find the hole, how do we find what that hole is? How do we find what that is? We'll get to that in a second. There's an algebraic way to figure out how do we figure out the hole in the graph. So before we get started here, any questions on the definitions for vertical asymptote, horizontal asymptote, or point of discontinuity? Remember, you have to know what it means in order to be able to solve it. Think back to what it was like in unit number 5 when we were dealing with end behavior. You can't solve it if you don't know what it means. So if you have questions, don't be afraid to ask. So let's look at example 1. So before we start doing this algebraically, we're going to look at a graph. So look at another example of a graph. So what we're going to do with this graph, we're going to find the vertical asymptote, which will allow us to find the domain. horizontal asymptote, which will allow you to find the range, and any point of discontinuity, holes in the graph. So, when you are doing the work yourself, don't feel as if you have to write out everything that I wrote out. So, vertical asymptote, you can label it as VA. That's good enough. Domain, obviously, you can use D with a colon. Horizontal asymptote, HA. Range, use R. For a hole in the graph, instead of saying point of discontinuity, put hole. So it's okay for you to use the abbreviations. I don't need you to write out the full term. If you want to, then you do you. But don't feel that you have to. So let's go ahead and analyze this graph. So vertical asymptote, we're looking for where's that vertical gap. It's real easy in this case because they drew it already for us. So they may not draw it for you all the time. You're just looking for a vertical gap, which was at x equals -2. So that means your domain, x cannot equal -2. So there's your vertical asymptote in your domain. Horizontal asymptote. If you're looking for where does the graph go flat? So this part is going flat right there. This part is going flat right there. So it looks as if it's flirting with 0. It's flirting with y equals 0. So horizontal asymptote is y equals 0. So your range is y cannot equal 0. Lastly is for any holes in the graph. So a hole in the graph means just that. If there's a hole in the graph, you identify it. So there's one right there. So that looks to be 2, comma, not quite halfway, maybe it's a fourth, so 0.25. So if it's not directly on a point, if it's not directly on a whole number, then give your best estimate. Give your best estimate. As long as you're not all the way ridiculously off, you'll get credit. So there's a graph, we took it apart. Any questions? Example 1. If you have questions, please make sure to ask because I can't read your mind. And I just get to assume that you know what you're doing. Yay me. All right, so let's look at the main things associated with analyzing a rational function. So analyzing a rational function starts with the zeros. Starts with the zeros. So these are all of the algebraic things that we need to know how to do in order to graph a rational function. If we can do all of these things, then it will make what we do next week that much easier. So if we do these things, it will make what we do next week that much easier. So we're going to start with zeros. So zeros means that will make the function equal 0. So examples 2 and 3 are two different scenarios. They're two different scenarios. So take f of x. 0 means that f of x has to equal 0. So 0 equals 2 over x minus 4 plus 1. So the easiest thing we could do is subtract 1 on both sides. So negative 1 equals 2 over x minus 4. Take negative 1 over 1. Take negative 1, make it a fraction. So now you can cross multiply. So now at that point you can cross multiply. Negative 1 times x minus 4 equals 1 times 2. So negative x plus 4 equals 2. Negative x equals negative 2. X equals 2. So you have a 0 at x equals 2. Any questions, example 2? All right. Example 3. We can technically do it the same way. Take f of x, set it equal to 0. So make the 0 a fraction. So this time when you cross multiply, 0 times x plus 6, well, anything times 0 is 0. So if you multiply these two together, that's 0. If you multiply those two together, nothing changes. So if you cross multiply, you end up with that. X squared means that it's a quadratic function. We're going to factor it. 3 terms is MAF. X plus 4 times x minus 3. So x equals negative 4 and x equals 3. So there's your two zeros. So just in case you forgot, zeros are the same thing as x-intercepts. These are points that would be on the x-axis. So if these were to be graphed, negative 4 would have a point on it, and so would the 3. Zeros are points on the x-axis. Any questions before we continue on? No, with zeros. If you have a question, don't feel free to ask. If you need clarification on something, please make sure you ask. Don't wait until you take a quiz or your unit test to then find out, oops, I don't know what I'm doing. My general test is a little late for me to help you then. All right. So vertical asymptotes, which is designed to help us with the domain. So as far as vertical asymptotes are concerned, remember, vertical asymptotes tell you where would the graph not exist? Where will the denominator equal 0? So for a vertical asymptote, take the denominator. Take the denominator, set it equal to 0, then solve. Take the denominator, set it equal to 0, and then solve. So with a basic rational function, x plus 5 equals 0. Okay, so x equals -5. Your vertical asymptote is x equals -5, which means your domain x cannot equal -5. X can't equal -5, that's that. Again, if you have questions, make sure you ask. Noah, Mackenzie, Nick, if y'all have questions, please make sure y'all ask. Do not walk out of here not knowing what you're doing. Vertical asymptotes, set the denominator equal to 0. So that rule applies regardless of what type of function it is. So this one's a little bit more complex. Oh, don't do it the same way. Take the denominator, set it equal to 0. In this case, it's x squared. So the quadratic function. Quadratic functions mean either A, you factor it, or B, you use the quadratic formula. You are much more likely to use factoring than you will the quadratic formula, or at least you're hoping so. So let's factor it. That's an MAF problem. So you end up with x plus 8, x minus 3. Remember, if you struggle with factoring, when you take your tests in class, you don't have time to try to go and look up everything, look up how do I factor this. You got to know how to factor. X factored, so x equals -8, x equals 3. Those are your vertical asymptotes, which means your domain x can't equal -8, and x can't equal 3. I didn't know it couldn't equal two things. Some of us haven't seen the country of Australia before, but it exists. You can have two vertical asymptotes. Just because it hasn't happened until now, it doesn't mean it doesn't exist. Questions on vertical asymptotes? All right, then let's switch to horizontal asymptotes. So these are the things associated with the range. So as you can see, if it's a reciprocal function, the horizontal asymptote is very easy. If it's a rational function, polynomial over polynomial, it's a little bit different. So, if it's just a plain reciprocal function, if it's a plain reciprocal function, then the horizontal asymptote is y equals k. Where is the k value? K is the number behind the fraction. K is the number behind the fraction. So in example 6, f of x equals 5 over x minus 4 plus 6. There's the number behind the fraction. So your horizontal asymptote is y equals 6. So your range, y cannot equal 6. Y cannot equal 6. It will flirt with that line, but it will never touch that line. So again, if it's a reciprocal function, it's pretty simple to deal with. Now, you have a full-on rational function, means you have a function at the top and a function at the bottom. That changes the game. It changes the rules a little bit. So, the horizontal asymptote is based on the degree. There's a word we have to use in a little bit. Of the P and Q functions. So that's the top of the fraction and the bottom of the fraction. Top of the fraction and bottom of the fraction. So, looking at 7, 8, and 9. So your degree, just a reminder, biggest exponent. Degree means biggest exponent. So if you look at 7, 8, and 9, the biggest exponent at the top is 2. The biggest exponent at the bottom is 1. So the degree at the top is equal to 2. The degree at the bottom is 1. For 8 and 9, let's do the same thing. The degree at the top is 1. The degree at the bottom is 2. For example 9, the degree at the top is 2. The degree at the bottom is also 2. So a degree means the biggest exponent. So that's a concept from unit number 5. So hopefully you haven't thrown away any of your notes, or you at least download them and save them. That way you have them. So each example lines up with one of these 3 scenarios. Each example lines up with one of those 3 scenarios. So, if the degree of the top is greater than the degree of at the bottom, so if the top is greater than the bottom, then you have no horizontal asymptote. So, top was 2, the bottom was 1. 2 is greater than 1. That means example 7 has no horizontal asymptote. So it has no horizontal asymptote. So that means there's no horizontal asymptote in your range. Your range is free. You're a free range then. So that's if the top is greater than the bottom. What if the top is less than the bottom? Then your horizontal asymptote is y equals 0. So 1 less than 2. So your horizontal asymptote is y equals 0. In your range is y can't equal 0. The reason for that is if the exponent is bigger at the bottom, then that means the bottom of the fraction is forever going to be larger than the top. So you're always going to be dividing by some big number, which eventually will just go to 0. That will become more and more evident for those of you who are going to calculus, because you deal with that a lot. But what if they're equal? If the top equals the bottom, then the horizontal asymptote is found by taking the leading coefficients and dividing them out. Take the leading coefficients and divide them out. So, the degrees were the same, so that means we take 4x squared divided by 2x squared. Well, the x squared will drop out, and 4 divided by 2 is 2. So y equals 2 is your horizontal asymptote. And your range is y cannot equal 2. So again, it's not a hard concept, but you have to understand what everything means. Once you understand what everything means, then solving out the problem is actually pretty simple. Any questions with horizontal asymptotes? All right, and the last thing that we'll look at with regards to analyzing a graph, getting everything set up for when we actually start graphing it next week, is what's called finding a point of discontinuity. So at the beginning, we had holes in the graph. So we had a hole in the graph. Now we're going to look at how did we get it? How did we get that hole in the graph? How did that hole in the graph come to exist? So here's how that hole in the graph came to exist. So, to find the hole in the graph, to find a point of discontinuity, simplify the rational function by factoring, canceling out the common terms. solve the common term for the given variable, and then use that value to evaluate the simplified expression. So it seems like a mouthful, but it actually isn't that difficult. So let's look at example 10. So example 10, x squared minus 7x plus 12 over x minus 3. And I'll color code it so that you can see what's going on. So, simplify the rational function by factoring, cancel out common terms. So f of x equals x squared minus 7x plus 12 over x minus 3. So if we factor that, you have x minus 4, x minus 3 over x minus 3. So that means the x minus 3s are going to drop out. X minus 3s are going to drop out. So you're left with x plus x minus 4. But first you simplify it. That's number one. Number two, solve the common term for the given variable. So the common term is whatever dropped out. So x minus 3 is the common term. So take x minus 3, set it equal to 0, and solve it out. So x equals 3 is the x value of the whole. It's a hole in the graph because that's what dropped out. So the third step, use that value to evaluate the simplified expression. So now you're going to take 3 and plug it in to your simplified expression. So x minus 4, you take 3 and plug it in, -1. So your hole, the hole in the graph is 3, comma, -1. So your hole in the graph is 3, comma, -1. Any questions? Example 10. Questions? Example 10. Any part that you got stuck on? We'll move through example 11. Perfect. So, last example follows the same rules. There's your function. So your first step, x squared minus 9, 2x squared plus 11x plus 12. Everything's got to get factored. So again, if you struggle with factoring, you got to practice it. You got to come in and get extra help if you need it. The top is difference of 2 squares. The bottom is MAF. The bottom ends up being MAF. Check it out, see if anything cancels out. So if you look at the problem, you notice that nothing drops. Nothing drops out. So first things first, make sure you factored everything correctly. Those are good. 2x squared, 8x, 3x, that's 11x, 3 times 4 is 12. Nothing drops out. So, since nothing dropped out, there are no holes in the graph. No holes in the graph. It is perfectly fine to have no holes in the graph. It is perfectly fine to have no holes in the graph. It is perfectly fine for that to happen. So when you're doing this on your homework, on your test next week, whatever the case may be, if you don't have any holes, don't think that you did the problem. It'd be that way sometimes. And these questions on examples 10 or 11. Oh. There aren't any questions, so we go ahead. So